Okay, here we go. Your first sets of identities. Some of these we discussed last chapter. Like your reciprocal identities, those first few. I know. Yeah, you got a couple of reciprocals there. Don't worry about if alpha is any integer or real. Don't worry about that. Just biggest thing to know, anytime you're dealing with tangent, tangent is the same thing as sine divided by cosine. We discussed that last chapter. So therefore, since cotangent is the reciprocal of tangent, cotangent would be equal to cosine over sine. Secant, also reciprocals. The secant of an angle is the same thing as 1 over the cosine of an angle. The cosecant of an angle is the same thing as 1 over the sine of the angle. And those kind of flow right into the second one. Now, here are your reciprocal identities. We've already discussed those. Sine is 1 over cosecant. Cosine is 1 over secant. Tangent, 1 over cotangent. And then the opposites of those. Okay, all work. And then you have what's called your Pythagorean identities. Pythagorean identities. These are really important. Identities. Sine squared plus cosine squared equals 1. I showed that one to you. And let me show you where these other ones come from. Because honestly, I have that first one memorized, and I can use it to kind of come up with the other two in my head. Sine squared plus cosine squared is equal to 1. Well, what if I went through and I divided everything by sine squared? That's legal. Let's use those other identities that we just discussed. Well, first off, sine squared divided by sine squared. Anything divided by itself, 1. Cosine squared divided by sine squared. Now, cosine squared, that's the same thing as cosine times cosine. And then sine squared is the same thing as sine times sine. What is cosine over sine? I told you a while ago, sine over cosine is tangent, right? What if you flip those two? What is from the top? What is cosine over sine? Cotangent. So therefore, this would be cotangent times cotangent, which is cotangent squared. So therefore, cosine squared over sine squared is cotangent squared. And what's 1 over sine? And that one of your reciprocal identity as well. Which one? Cosecant. So using my first Pythagorean identity, sine squared plus cosine squared is 1. I also have a relationship, and what an identity is, I guess I need to go into that. An identity is simply a relationship amongst all your trigonometric ratios. If I know sine, I know cosine, and I know tangent, because there's that relationship there. Tangent is sine divided by cosine. If I know sine, then I know cosecant, because it's got a relationship between the two. Cosecant is simply 1 over sine. Sine is simply 1 over cosecant. There's that relationship. Here you have a new relationship. 1 plus cotangent squared is cosecant squared. So what if I've got the cotangent of an angle? Can I go from cotangent to cosecant? Yes, using this identity. The identity is simply a relationship or a formula connecting two trig identities, or two trig functions. How many identities are there? Millions. Millions. Are we going to learn them all? No. We learn the most common ones. Okay? You can find a formula that relates to, you can relate sine and cosine to probably cosecant. I mean, there's all sorts of formulas out there, but we're going to learn the most basics. Now, if you took the exact same formula, sine squared plus cosine squared equals 1, which, by the way, does come from the Pythagorean identity. That's where this whole formula comes from. If you took the exact same formula and now instead of dividing everything by sine squared, divide everything by cosine squared. And you're going to come up with a different identity. What's sine over cosine? Tangent. So sine squared over cosine squared would be tangent squared. Plus cosine over cosine is 1. 1 over cosine is secant. So there's another one. And that's those two there. That's the last two I have listed here. So if you haven't already got them written down, make sure you copy down your Pythagorean identities. Okay. Actually using identities. First thing we're going to use our identities for is to simplify expressions. The same way you go back and when we did rules of exponents. The same way that you had rules of exponents that you could use to simplify this expression, we know that we can reduce fractions. We know that when we have X's over X's, different exponents we subtract, and we know how to move negative exponents. The same way we had rules for exponents, we also have rules for trigonometry. We have rules for identities. Well, actually, the identities are our rules. Tangent divided by secant. Now, what we're going to use the identities that we already know, the identities that we just listed. We're going to use those identities to clean up and to really create new identities. My advice for you, when trying to clean these things up, what I do personally, I try to get everything in terms of sine and cosine. I try to stay away from secants, tangents, cotangents, cosecants. I try to get everything as either a sine or a cosine identity. So on top here, the tangent of x. What can I turn tangent of x into? Sine over cosine. So on top, I took my tangent of x, I turned it into sine over cosine. Over. On the bottom, I have secant. From that list we just made, what's secant equal to? 1 over cosine. Try to turn everything into terms of either sine or cosines. And from there, clean it up. You got two fractions being divided. In order to divide fractions, we flip and multiply. So now I have sine. And let me show you. On this, if you don't want to put the x every time, that's just your argument anyway. You're just dealing with sine, cosine. You don't have to put that x. Okay. Now, once you put your final answer, I really would like for you to put it back in. But as you go, honestly, you could put big S, big C or something if you want to, just as you clean it up. Flip and multiply. Cosines cancel, and you're left with sine of x. So is that an identity? Yeah. You have to memorize it? No. No. Like I said, there's millions and millions of identities. The relationship between tangent and secant. The tangent of 30 divided by the secant of 30. If for some reason you had that in the problem, the tangent of 30 divided by the secant of 30 is 1/2. How do I know that? Because it's the same thing as the sine of 30. That's what that identity states. The tangent of an angle divided by the secant of that same angle is equal to the sine of that angle. Next one. Sine of x plus cotangent of x times the cosine of x. Let's leave sine and cosine as is. But cotangent, let's turn it into cosine over sine. And then we got that times the cosine. And before I can multiply two fractions, I'm going to put a 1 on bottom. So multiply the tops, multiply the bottoms. Turns this into the sine plus, what do y'all think? Cosine times cosine. X times x, y times y, z times z, cosine squared. And by something else, I guess I need to address this. I'm not going to put the x, but when you have cosine squared, I know this is weird, you put the squared on the cosine, not on the x. Okay? The relationship, the difference between these, if you have cosine of x squared and the cosine squared x, the first one, what's being squared, is just the x. The second one, what's being squared, the whole cosine x. Okay? If you want your answer squared, now you could do it like this. If you want to put that whole thing in parentheses, then that's the same thing. But anytime it's the whole cosine stuff being squared, you put it on just the cosine there. And that means not the x being squared, but the whole thing. But I guess we kind of addressed that a while ago with Pythagorean identities. So you have sine plus cosine squared over sine. I'm confused. I don't know. Is there anything else I can do here? What I'm going to do, I'm going to find a common denominator. Okay. We're going to try to add these two things together, and you're going to see what's going to happen. Sines over 1. But to get a common denominator, I need a sine on bottom here. What do I multiply top and bottom by? Sine. So now I've got a sine on bottom, and I have a sine squared on top. Let's see how I did that. Multiply top and bottom by sine. Now I can add them. And when you add them, you have sine squared plus cosine squared over sine. Jackson, look back at your notes. And we just wrote down something about sine squared plus cosine squared, did we not? Yeah. Anytime that you see sine squared plus cosine squared, that's equal to 1. So therefore, this whole thing turns into 1 over Sine, which also looks familiar. I'm not going to circle that. That's not the answer. That 1 over sine also looks very familiar. That's one of our identities. What's 1 over sine equal to? Cosecant. So all of this turns into cosecant of x. So is that another identity? Yes. If you wanted to find the sine of 45 plus the cotangent of 45 times the cosine of 45, the easiest way, just find the cosecant of 45. The sine plus cotangent cosine of an angle is equal to the cosecant of that angle. Same thing. And here's another one. Simplify tangent of x times cosecant of x times the secant of x. Tell you what, take a little bit of time, try that one around. Michaela, the first one, tangent x. What'd you turn it into?
Sine over cosine.
Good. So we have sine over cosine times, Michael, what'd you turn cosecant into?
1 over sine.
1 over sine. All over, and then on bottom we've got secant. Drake, what'd you turn secant into? 1 over cosine. And now it's just cleaning all that stuff up. Again, tangent times cosecant divided by secant. Multiply the top together. Austin, what happens? And you're left with 1 over cosine. Divided by 1 over cosine. Now, you can think about it. Anything divided by itself. Or if you want to go through the steps, flip and multiply. You're going to have 1 over cosine times cosine over 1. Cosines cancel, leaves you with 1. All that stuff equals 1. If you don't believe me, well, I'll show you. Watch this. Pick any angle, because this formula should work for any angle. That's the x is just a general angle. I'm going to make sure I'm in degree mode because I want to. Yeah. Let's do the tangent of 45 times the cosecant of 45. Let's see, to do the cosecant of 45, I'll have to do times 1 over the sine of 45. 1 divided by sine 45. And then that whole thing divided by the secant of 45, which is 1 over the cosine of 45. Because that's the only way you can type in secant and cosecant to your calculator. And look, final answer, 1. You can use 45 degrees, use 30 degrees, use 28.5 degrees. No matter what angle you plugged into that, you always get 1. That's equal to 1. That's kind of like saying x divided by x. Cleaning it up, x divided by x is always equal to 1. Write an identity that expresses the tangent function in terms of the sine function. Write an identity that expresses the tangent function entirely in terms of the sine function. Well, tangent. First off, I know tangent is equal to sine over cosine. But what I want to do is I want it expressed entirely in terms of sine. So we're halfway there, right? I just need to somehow turn that cosine stuff into sine stuff. So you would think, okay, is there any relationship between cosine and sine? What do you think? Is there? What is your relationship between sine and cosine? What identity relates sine and cosine? Sine squared plus cosine squared equals 1. That's the relationship between sine and cosine. So I'm going to somehow use that. I want to get rid of all my cosine stuff here. I want it expressed entirely in just sine terms. So I need something to plug into cosine that's going to turn it into sine. Well, let's take and manipulate this a little bit. And turn it into, or find out what is cosine equal to in terms of sine. Well, first let's take and move our sine squared over. So I know cosine squared is 1 minus sine squared. Still don't have anything I can plug in for just cosine. I have cosine squared now. Get rid of the square by square rooting. Cosine is equal to plus and minus the square root of 1 minus sine squared. There's what cosine is equal to. So now I can go back up here. Tangent is equal to sine, we'll use x, divided by plus and minus the square root of 1 minus sine squared x. So if you've got the tangent of an angle, you've got the tangent of 30 degrees and you don't want to find out what the sine of 30 degrees is. What can you do? You can use this formula that we just made up. You could do the sine of 30. To find out what the tangent of 30 is, you could do the sine of 30 divided by plus and minus 1 minus sine squared 30. So this whole chapter is just going to be pretty much taking those identities that we learned and just using them. And then they're going to present new identities to you, and you're going to take them and use those. So pretty much, if you're kind of catching on to what we're doing now, this chapter will be pretty easy to you. Here we go. Given that the tangent of alpha is equal to negative 2/3, and alpha is in the quadrant 4, which, I mean, take tangent's negative. We knew that is either in quadrant 4 or quadrant, where else is tangent negative? Here, 2. So they tell us we're in quadrant 4. Now, why is that important? They're about to say, okay, tangent's negative 2/3, we're in quadrant 4, find the remaining 5 other trigonometric values by using identities. We've done this before. Okay, there's other ways of doing it. I'm going to show you both ways because honestly the other way without identities is a little bit easier. But the reason they tell you we're in quadrant 4 is we need to know, are those other identities going to be, or excuse me, are those other functions going to be positive or going to be negative? And since we're in quadrant 4, all students take calculus. Cosine is the only, now careful there, cosine is the only primary trig function that's going to be positive. Since cosine is positive, then what else will also be positive? Secant. Okay, so keep that in mind. So we got tangent, excuse me, tangent is negative 2/3. And again, you can put the alpha if you want to, but you don't have to. Tangent is negative 2/3, and we want to figure out what the others are equal to. Well, tangent is equal to sine over cosine. We've got that one, but the only problem is, what are you going to do with that? You've got two unknowns there. You don't know what sine is, you don't know what cosine is, so we've got to have some other route. What was that other identity involving tangent? When the tangent squared? What was it? The Pythagorean identity? Plus 1 equals. So what we can do is we can take this tangent answer and we can go to secant. That makes sense. We have a relationship between tangent and secant here. So since tangent is negative 2/3, just plug it in right here. So you have negative 2/3 squared, which is 4/9, plus 1 equals secant squared. Everybody good there? Solve the equation, and you've got secant now. 4/9 plus 9/9. Add those together gives you 13/9 is equal to secant squared. To get rid of a squared, we're going to do plus and minus the square root. But again, plus and minus there, we can fix that. We're in the fourth quadrant. Cosine is positive, so secant will also be positive. So we can kind of dump the plus minus, we know it's positive. And instead of the square root of 13 over the square root of 9, let's leave that as the square root of 13 over, we know the square root of 9 is 3. So there's 1. So we have the secant of alpha would be root 13 over 3. Since we have secant, what else do we have? Good. The cosine of alpha is simply the reciprocal of that. You'll see all these relationships that we've got going on now. Secant is root 13 over 3, so cosine would be 3 over root 13, which we do have to rationalize. Multiply top and bottom by root 13, that'd be 3 root 13 over 13. So there's secant and cosine. Does anybody have another easy one we can get from tangent? Tangent automatically goes with what? Cotangent. If tangent is negative 2/3, then cotangent will be negative 3/2. Well, let's just circle that. Because they're reciprocals of each other. So now we have tangent, cotangent, secant, cosine. We need sine and cosecant. And if I can find sine, I know all I got to do is flip it to find cosecant. Because they're reciprocals of each other. How can I go from these to sine? Any ideas?
1 plus cotangent squared equals.
Well, we did that for secant. Oh, 1 plus cotangent squared, you said. There's about 3 different ways you can do this. If you want to, you can do 1 plus cotangent squared equals what? cosecant squared. Oops. Everybody good with that? And here's cotangent, plug it in there. Could I use tangent equals sine over cosine? No. Do we know what tangent is? Sure. Do we know what cosine is? Sure. That's kind of ugly. Okay. Since we know tangent and cosine, now let's manipulate that a little bit. How do I find sine? Can I move the cosine over here? Is sine not equal to tangent times cosine? Just since it's divided by cosine, move it over by multiplying. So if I have tangent and cosine, could I not multiply tangent and cosine together to give me sine? Is that an identity? Yeah. Is it one that we're going to memorize? No. Okay. There was a third way. What was the third way? I was just thinking about how to do it another way. Let me think. That might have been the only two there. Let's use his method. I kind of like it. Let's use his method here. 1 plus cotangent squared, which would be 1 plus, the cotangent is negative 3 over 2, so cotangent squared would be positive 9 over 4 equals cosecant squared. 4 over 4 plus 9 over 4 is 13 over 4 equals cosecant squared. To get rid of a square, we do plus and minus the square root. So cosecant is plus or minus the square root of 13/4. Since we're in the fourth quadrant, cosecant will be negative. The negative square root of 13 over the square root of 4, which is 2. So we now have cosecant. Cosecant of alpha is negative root 13 over 2. And to find sine, we simply flip it. The sine of alpha would be negative 2 over root 13. Rationalize would be negative 2 root 13 over 13, which is the exact same answer you would have got by using the sine, cosine, and tangent. Now, again, I told you we was going to look at it the other way, just to show you, because this way is so much easier. If you want to work it this way, especially on ACT type test, because these questions are on there, promise. Okay, these type. Given that the tangent of A is negative, or tangent of alpha is negative 2/3, and you're in the fourth quadrant, what I do is I draw me a little. There's my angle. I don't know what the angle is. Now you can find it. Y'all remember doing this? Move the tangent over by doing inverse tangents. You can do the inverse tangent of negative 2/3. It's going to give you an angle. Okay, it's actually going to give you a negative. Let me think. Yeah, tangent is defined from negative 90 to positive 90, so it's going to give you a negative angle here. And you could go through and you can find, okay, what if the angle is negative 30? Then you could go through, okay, then find the sine of negative 30, find the cosine of negative 30. You could do that, but there's easier ways. This will give us exact answers. We're in the fourth quadrant. I'm not sure what the angle is, but I don't have to. Draw you a little right triangle. I know that tangent is opposite over adjacent. Here's the angle. That's my reference angle. Tangent is opposite over adjacent. So look, negative 2/3, there's opposite and adjacent. Now, I don't put negatives on there because honestly that whole all students take calculus thing, that takes care of the positives, negatives. So pretty much I have some point here. Okay, opposite, adjacent, I go out 3, I go down 2. That's my opposite side, my adjacent side. By Pythagorean theorem, which notice, didn't we use Pythagorean identities to find this? There is that relationship there. That's where the Pythagorean identities come from. By the Pythagorean theorem, a squared plus b squared is equal to c squared. A squared is 9, b squared is 4, so c squared would be 13, so c would be the square root of 13. And just by using all students take calculus, you can find your other angles there, or your other functions. Sine, I'll just do a couple. The sine of alpha, since we're in the fourth quadrant, will be negative, and will be opposite over hypotenuse, which will be negative 2 root 13 over 13, same answer we got. If you wanted to find cosecant, or let's do secant, the secant of alpha. Well, secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant would be hypotenuse over adjacent. So hypotenuse over adjacent. And since you're in the fourth quadrant, secant will be positive. See, that's a whole lot easier. Much easier than use identities. Why do they want you to use identities? Honestly, just entirely for practice. Because if you're solving that type problem, that's a whole lot easier. Use your Pythagorean theorem, find your hypotenuse there, and go with it from there. Okay, much easier. We're not going to work another one of those. Here's your next type of identities called odd and even identities. Honestly, back in the back of your mind, you already know these identities. It all has to do with your all students take calculus 4 quadrants. As you're writing these down, let's go back and review what an odd function is and what an even function is, because that's where we're going with this. An example of let's start with an even function. An example of an even function, the most basic even function there is y equals x squared. Now, what's special about even functions? Do you remember? They have some type of symmetry. What's your symmetry here? Where is it symmetrical? Y-axis. Even functions are always symmetrical across the y-axis. What about odd functions? Your basic odd function, one of your most basics, is y equals x to the third, which I told you looked very similar to tangent, didn't it? Is tangent going to be an odd function? Yeah. See it right there? And we have rules. Our rules was for an even function, the sine of x, or excuse me, not sine, goodness, already getting ahead of myself. For an even function, f of x was equal to f of negative x. F of 3 and f of negative 3, remember that? F of 3 was here, f of negative 3 was here. F of 4 was here, f of negative 4 was here. That was your basic rule for even functions. F of x was the same thing as f of negative x. For even functions. For an odd function, f of negative x was equal to the negative f of x. That was the rule. That's how we determined whether something was an odd function. Now think about what we did with sine, cosine, and tangent. And the other three are going to follow suit. Think about the graphs of those things. When we graph sine of 0 was 0. And then it did this number, right? Just like girl's hair. Let's say the girl's hair. Is sine an even or an odd function? You see that there? You see that symmetry going on across the y-axis? Sine's an even. Sine's an, excuse me. Sine, no, I'm way off. Cosine, my bad. That is not sine, that is cosine. Cosine of 0 is 1. I said it right, and then I graphed it wrong. Cosine of 0 is 1, and then you've got, because that threw me off. Cosine is an even function because it has y-axis symmetry. What else does that tell us? That tells us that the cosine of negative x is equal to the cosine of positive x. F of negative x is equal to f of positive x. And you can do the same thing with sine and tangent here. If you think about what the graph of sine looked like. Sine of 0 was 0, and it did this number. And then it came over here and did this number. Does that not have rotational symmetry? If I spun this thing 180 degrees around the origin, do I not get the exact same graph back? So sine, and you can do the same thing with tangent, sine and tangent are odd functions, meaning that the sine of negative x is equal to the negative sine of x. That's our test for odd functions. So what does that mean? In a nutshell, honestly, guys, if you want to find the cosine of negative 30, then you can dump the negative. That's all it means. If you're finding the sine or tangent of negative 30, then you can pull the negative out front and not worry about it anymore. Okay, that's what even and odd functions. And again, if it works for sine, it works for cosecant. If it works for tangent, it works for cotangent, and the same thing for cosine and secant. Okay, so let's work some identities with these. Solve a few more, and then we'll stop for the day. The sine of negative x. And honestly, as far as memorizing these, yeah, you kind of need to know them in the back of your mind. Sine of negative x. Again, with sine and tangent, you can pull them out front. Sine and tangent are odd functions. So therefore, the sine of negative x, what I'm going to do is I'm going to rewrite that as the negative sine of x. Now, these identities that I just gave you, that's right there is in a nutshell how you're going to use them. Anytime you see the sign of a negative x or negative angle, pretty much do you leave it there? Do you drop it? Do you pull it out front? That's what you can do with it. Times. What about the cotangent of negative x? What do I do there? How do I rewrite the cotangent of negative x? Good, put the negative out front. The negative cotangent of x. Negative times negative cancels. So pretty much I can dump them there. Let's clean it up a little bit more. Now it turns into an old first section stuff. Now I've got the sine times, and I don't worry about the x's anymore. The sine times the cotangent, which is cosine over sine. Sines cancel, leaves me with the cosine of x. So pretty much these odd-even identities tell you what to do when your angles are negative. Second one. 1 over 1 plus the cosine of negative x. What can I do with cosine of negative x? Just drop the negative completely. So cosine of x. And then plus 1 over 1 minus cosine of x. That one doesn't have 1. That doesn't have a negative on your x. And here's the one that gives people issues for some reason, because we somehow when we add these together, we're wanting so bad just to maybe multiply by -1 or something so we can make those bottoms the same. Before you can add those together, you have to have a common denominator, which in order to do so, I need to erase some of them here. I need the space. Because what in the world is our common denominator going to be? Does anybody know? Give me a second, think while I'm moving it. One-third plus 1/4. Maybe back in 7th and 8th grade you had trouble with common denominators and the teacher gave you a shortcut. If you can't think of a common denominator, what can you always do? Just multiply them together. So what's the common denominator here? I mean, and honestly, this is actually the least common denominator as well. This stuff times this stuff. So what I'm going to do, and unfortunately you don't have the luxury of this. Well, I might not even. Let's see. Nope, I can't. I was fixing to just move that over. It'd be real nice. I'm going to multiply top and bottom, like here. Multiply top and bottom by 1 minus cosine x. Over here, I'm going to multiply top and bottom by 1 plus cosine of x. And something pretty cool happens. So now I have multiplied top and bottom by 1 plus cosine of x. I now have 1 minus cosine x. I have 1 minus cosine x over 1 plus cosine x times 1 minus cosine x. I'm going to go ahead and dump those x's. Less writing. There we go. Any questions there? Plus, I'm multiplying top and bottom by 1 plus cosine x, so now I have 1 plus cosine x over 1 plus cosine, 1 minus cosine. By the way, what is 1 plus cosine, 1 minus cosine? What do we call those? Conjugates. And y'all remember how to multiply conjugates together. So now we've got common denominators. We can add the tops together. Do you see what happens to negative cosine, positive cosine? They cancel. So I have a 2 on top. And on bottom, this stuff turns into, let's multiply those together, make it look a little bit better. I don't have to worry about insides and outsides. To multiply conjugates, you multiply first and first, and you multiply last and last. And I have 2 over 1 minus cosine squared, which a lot of people will circle. So, you got one more step. My advice for you, anytime you're dealing with a sine squared, a cosine squared, a tangent squared, a secant squared, a cosecant squared, as of right now, you really only have one identity that deals with squares. And those are one set of identities, and those are called the Pythagorean identities. Sine squared plus cosine squared equals 1. Tangent squared plus 1 is equal to secant squared, right? And your third one. But that doesn't, it kind of resembles that, right? But it's not identical. Move that over. Anytime you've got 1s and sine squares, or 1s and tangent squares, or 1s and cotangent squares, more than likely you can turn that into something else. If you move cosine squared over, does that not turn into 1 minus cosine squared? And it's going to be equal to sine squared. You'll see that? So I could rewrite this if I wanted to as simply 2 over sine squared. Okay, here we go. Next one, simplify cosecant of negative x, tangent of negative x. First thing, since you're dealing with negative angles, you have to look and see, are those odd identities or are they even identities? The cosecant of negative x, cosecant goes with sine. I know that sine, by the nature of its graph, which I don't know if you have to go through the same thought process I do. Sine, by the nature of its graph, is an odd function. Since it's an odd function, then cosecant or sine of negative x is equal to negative sine of x. I can pull that negative out front. So I'm going to take cosecant of negative x and write it as the negative cosecant of x. Times. What about tangent? Do you drop it or do you move it out front? Yeah. Negative tangent x. And that from here down, I'm not going to write that x anymore. It's a waste of lead. Negative times negative is a positive. If one of them was a negative and the other was a positive, then you just leave the negative. Cosecant is 1 over what? Good. And tangent is
Sine.
good. Everybody good with that? What happens?
Sine.
Left with 1 over cosine. What is 1 over cosine? So that is equal to the secant of x.